Fresh updates from the fringes of our solar system. The comet 3I Atlas is defying expectations as a typical icy body. Just days back, stargazers observed this visitor from beyond our system, slipping within 2 astronomical units of the Sun, where it started glowing much brighter than forecasts suggested. Its surrounding haze has ballooned to half the size of our Sun. The light it emits has turned to an eerie green hue, and in the strangest twist, it's grown a tail aimed straight at the Sun, a phenomenon that defies all logic. Hurtling toward Mars at incredible velocity, scientists confess they're baffled by the spectacle. The timer to its closest solar pass has started ticking. With each moment that passes, this extraterrestrial traveler seems less like an ordinary comet and more like an enigmatic puzzle from the cosmos, urging us to uncover its secrets. Stick around through this evening's deep dive to discover how this unfolding event challenges our understanding of the universe and what unfolds when interstellar substances stir to life. First segment, it's expanding and intensifying. The data speaks volumes even as it challenges our grasp. During mid-September 2025, experts tracking 3I Atlas spotted a disturbing anomaly in their readings. The luminosity readings surged past the anticipated lines, jumping from the forecasted magnitude of 15 or 16 up to a surprising 12 to 14. For anyone new to the inverted scale of stellar brightness, this marks a huge leap. Picture it like this. In astronomy, magnitude values decrease as objects shine more vividly. The smaller the figure, the more radiant it is. A mere 2-point decline indicates the body is now beaming out 6-fold the light over expectations. Yet this shift wasn't slow and steady. It was a rapid escalation. The Comet Observation Database, or COBS as enthusiasts call it, started displaying points that rose persistently beyond the usual warming trajectory for such objects. Observations from Earth's observatories backed up the pattern. 3I Atlas was surpassing all the computational models built for its sunward path. The turning point arrived when the entity dipped inside about 2 astronomical units from the Sun during early to mid-September. To put it in perspective, 1 AU equals the Earth-Sun separation, about 93 million miles. At that range, 3I Atlas remained twice as distant from the Sun as our planet. Still, a core transformation occurred. The pace of its brightening surge went beyond surprise. It was downright worrisome in scale. What might trigger such a sharp rise in brilliance? The prime theory points to volatile frozen elements like carbon dioxide ice, water, and unusual substances trapped in its core. Having originated near a distant star, as the Sun's rays grow stronger, these components don't simply thaw. They burst from solid to vapor, hauling along particles and grit while forming vast sunlight-scattering vapors. But this is the part that raises eyebrows. Such quick flares in visibility frequently hint at volatility. Icy bodies undergoing abrupt gas releases risk breaking apart, spawning several fragments or dazzling rubble veils. They might also deplete their reactive stores swiftly, resulting in just as sudden fades. That 3I Atlas is outpacing projections in its glow-up implies we're observing mechanisms beyond current scientific insight. No need for widespread alarm over our world. That said, NASA verifies that 3I Atlas will keep a secure berth, staying at least 8 astronomical units from Earth, almost double the span to the Sun. The worry isn't impact, it's interpretation. We could be seeing an ancient interstellar relic transform before our eyes as it charges into the solar system's core. Ponder the ramifications. This entity coalesced from wreckage orbiting a far-off star, possibly centuries of light-years distant. It formed from stuff untouched by our Sun's heat, unexposed to the unique forces that molded local space rocks. But now, in its lifetime's debut, it's facing the harsh radiation of our inner realms. The luminosity spike might signal long slumbering reactions firing up after eons or epochs. Rare frosts, steady in the cold voids between stars, could be vaporizing anew since their inception. This might reveal molecular traces from a foreign stellar realm, kept pure over galactic expanses. The schedule adds extra pressure. 3I Atlas nears key milestones that will shape what observers glean from this rare intruder. On October 3rd, it swings nearest to Mars, just 30 million kilometers away, near enough for probes around the rusty world to catch sights hidden from our vantage. Come late October, on the 29th to 30th, the comet hits perihelion, its sun closest point at roughly 1.36 to 1, 4 astronomical units. Here's where things get concerning for those of us watching from Earth. As the comet known as 3I Atlas approaches our sun, its location in the heavens drifts perilously near the star's intense radiance. Starting in early October and lasting until early November, it passes through what's termed superior conjunction by stargazers, a phase where the sun's dazzling light renders viewing from our planet's ground virtually out of the question. Consequently, the height of this cosmic intruder's display, when sunlight's warmth hits its fiercest and the object's secrets could come to light, will mostly evade our direct sight. Instead, we'll depend on the unblinking sensors of probes scattered across the solar system, especially ones circling Mars, to capture what might rank as the grandest showcase of alien chemistry ever seen by humankind. The ongoing increase in luminosity implies that 3I Atlas won't slip past its closest solar approach without a fuss. Recent sightings indicate an entity invigorated by its brush with our star, perhaps gearing up for explosive surges that could unveil hidden aspects of its makeup and form. Yet, will these disclosures happen amid the stretch when our ground-based scopes are overwhelmed by the sun's brilliance? Insights from September's data depict an item undergoing change. Brightness readings surpassing expected patterns reveal that 3I Atlas is evolving into something distinct from its state during the vast trek across interstellar voids. The puzzle remains. Does this shift reflect typical cometary actions in an unusual specimen, or is it wholly novel compared to our encounters with outsiders from distant stars? In the next few moments, we'll delve into the reasons behind this body's expansive coma that stretches beyond normal limits, the oddity of its tail aiming sunward rather than trailing behind, and the implications of its latest turn to a strange verdant hue, which could point to unseen reactions in an interstellar traveler. The enigmas are piling up as rapidly as the light levels are rising, but before anything else, it's essential to grasp what this thing truly is, because 3I Atlas transcends ordinary comets. It's merely the third verified arrival from beyond our solar system, and its antics are already demonstrating that every such wanderer follows its unique playbook. Part 2. Discovery and Classification. The tale of 3I Atlas kicks off atop a Chilean peak where automated scanners probe the darkness with robotic accuracy that outstrips human efforts. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System Atlas in brief picked up a dim patch of glow shifting amid the fixed stars. At first, logged as yet another small solar system resident, this modest detection would quickly reshape our knowledge of cosmic interlopers. Defining an interstellar body goes beyond its distant birthplace. It's the ironclad orbital proof that it can't get trapped in our sun's gravitational pull. 3I Atlas traces a hyperbolic orbit, as experts describe it, a route brimming with such speed that after looping around our star, it'll head out eternally, unbound and gone for good. The calculations of its path are ruthlessly exact. This visitor packs excess momentum to succumb to solar tug. The 3I label carries its own narrative. The I denotes interstellar, with 3 marking it as just the third such find in recorded history. Its forerunners, one I Oumuamua in 2017 and 2 I Borisov in 2019, each stunned scientists with traits that resisted simple labels. Now, 3I Atlas upholds this legacy of cosmic caprice from afar. Spotting these rarities underscores their elusiveness. Atlas runs from the Riuardo Observatory in Chile's Atacama Desert, integrated into an international array aimed at flagging risky rocks nearing our world. It snaps repeated shots of sky patches in quick succession, then employs software to pinpoint movers against the starry canvas. That July evening, 3I Atlas showed up as scarcely more than a vague line, hardly set apart from the myriad asteroids, comets, and orbital junk crowding our sun's nearer realms. However, follow-up archive scans, prior snaps displaying the body pre-discovery uncovered that 3I Atlas had been hiding in astro records for weeks, unnoticed in its import. Such late acknowledgement often plagues interstellar finds, which typically look rocky at first glance, before sprouting the hazy envelopes and streams that identify them as cometary. The early evaluation spotted a subtle coma encircling the core nucleus right away, hinting that 3I Atlas was far from a mere stone. Comets form these hazy comets develop their distinctive fuzzy envelopes, known as comas, when sunlight warms ices, prompting them to vaporize and form expanding layers of gas and dust. Detecting a coma at such a remote distance from the Sun, 3I Atlas was over 3 astronomical units away at the time of its initial spotting reveals that this body holds volatile substances able to release gases even in the frigid outer zones of our solar system. Word of the find quickly circulated among astronomers, prompting major observatories to redirect their focus to this fresh, extragalactic guest. In July, the Hubble Space Telescope snapped high-resolution photos, complemented by data from the Very Large Telescope in Chile and various other earthbound facilities. Further examinations uncovered a far more intricate entity than the first glimpses had implied. Determining the dimensions of 3I Atlas stays elusive and challenging, a typical issue for dim, far-off targets that resist straightforward sizing. An August refinement from Hubble constrained the core's potential scale to between voyage 3 and 5, 6 kilometers across, highlighting the hurdles in distinguishing the dense heart from its enveloping haze. This ambiguity in scale carries weight, as it influences estimates of the body's weight, compactness, and resilience against the Sun's fierce warmth as it draws nearer. Velocity assessments offer a sharper view of the visitor's exceptional traits. Hurtling along at about 130,000 miles per hour, or roughly 58 kilometers, 3I Atlas exhibits paces that outstrip any innate motion within our solar system. By contrast, Earth's path around the Sun proceeds at a leisurely 30 kilometers. The incoming object's velocity will ramp up further from the Sun's pull as it nears perihelion, possibly hitting 68 km or exceeding 150,000 mph. Such blistering rates emphasize the outsider's otherworldly essence. Nothing originating in our solar system could attain these without boosts from planetary gravity assists. 3I Atlas bears the momentum marks of its cosmic voyage, built up over eons crossing the galaxy amid stellar pulls and galactic spin. With so few verified interstellar wanderers, every discovery holds immense value for research. Prior to 2017, experts relied solely on simulations to anticipate how such drifters might act on long-haul trips between stars. Oumuamua upended numerous expectations through its cigar-like form and odd thrust without gravity's aid. Tuyi Borisov looked more like a standard comet, yet displayed molecular makeup alien to our system. 3I Atlas now contributes a third case to this limited archive, with preliminary signs pointing to distinctiveness matching its forerunners. Its actions test existing frameworks in fresh directions, especially the surprisingly expansive coma and atypical shifts in luminosity. Every such interloper brings its unique physics and chemistry, implying the galaxy teems with greater variety in crafting minor bodies than once thought. Categorizing it goes beyond verifying its interstellar roots. Scientists need to assess if 3I Atlas qualifies as an asteroid-type rock, a comet, or an outlier. The coma points toward cometary traits, yet detailed gas and particle profiles from spectra will clarify its origins and development in its home stellar setup. This isn't some homegrown comet nudged in from the Oort cloud, that remote stockpile of frozen remnants that sporadically dispatches probes to our inner realms. 3I Atlas coalesced near a different sun from stuff shaped by alien thermal, pressure, and reactive conditions unlike our local setup. It offers a raw glimpse into world-building dynamics from light years distant, perhaps eons past. Path projections for 3I Atlas promise rare viewing windows, especially near its Mars flyby on October 3rd. This setup proves serendipitous. The orbit's tilt and schedule suit probe scrutiny right as ground scopes face interference from solar brightness. Yet grasping the spectacle demands more than tracing origins and destinations for 3I Atlas. The true enigmas center on its reactions to our sun's rays, its debut exposure, and the stark deviations from expected patterns. Part 3. Path and Schedule. The clock ticks fast for 3I Atlas, and the observer's hustling to decode it before sunlight swallows it whole. Orbital math charts a clear course through the inner system, pinpointing key dates ahead will shape the insights humanity gains from our third verified interstellar guest. The initial pivotal moment arrives on October 3, 2025, when 3I Atlas glides by Mars at about 30 million kilometers away, equivalent to roughly 19 to 0, 2 astronomical units. In the grand scale of the cosmos, this qualifies as a remarkably near pass, bringing the spacefarer squarely into the detection zone of several probes circling the reddish world. The scheduling feels both incredibly timely and deeply aggravating. Right when 3I Atlas hits its nearest point to Mars, granting orbiters the sharpest vantage on an extrasolar body in motion, ground telescopes on Earth start struggling to follow its path. The harsh realities of orbital dynamics position the comet ever nearer to the sun's spot in our heavens, spawning viewing hurdles that will quickly turn impossible to overcome. Toward the end of October, from the 29th to the 30th, 3I Atlas achieves perihelion, its minimal distance to the Sun at around 1.36 to 1, 4 astronomical units. At this range, it slips just shy of Mars's typical orbital path, exposing the interstellar wanderer to levels of solar energy far beyond what it faced while traversing the galaxy. This phase aligns eerily well with the height of viewing woes from our planet. The progression of its speed paints a compelling narrative all its own. Presently cruising at dozens of kilometers per second, 3I Atlas will hit peak swiftness close to perihelion, possibly surging to 68 kilometers, or about 152,000 mph. For context, our world holds its steady loop around the Sun at around 30 kilometers. Thus, 3I Atlas will outpace our planet by more than double. Such paces aren't mere numbers to marvel at. They highlight the core principles driving motion across the stars. In contrast to solar system locals, whose velocities built up via gravitational tugs from the Sun and worlds over eons, 3I Atlas bears the momentum gathered on its voyage between stellar realms. Each kilometer per second embodies immense spans crossed in the void of space, shaped by the pulls of various stars and the galaxy's spin. Its incoming route situates 3I Atlas close to the ecliptic plane, that slim disk holding most of our planetary paths. Such positioning eases the tight brush with Mars and sets up a remote flyby of Jupiter in 2026. This lineup isn't by chance. Incoming bodies from arbitrary angles in 3D space rarely thread so neatly past several planets on their short jaunt through our system. Risk assessments played no role for 3I Atlas, even though early scans tagged it as a possible hazard. Its minimal approach to Earth stands at about 1.88 astronomical units, almost double the Sun's reach and far removed from any danger. NASA's validation of this secure gap quelled worries over impacts, freeing scientists to prioritize discovery over safeguards. The true hurdle stems from sighting angles. From the start of October into early November, 3I Atlas endures what's termed superior conjunction by stargazers, a stretch where its sky position hugs the Sun too tightly for feasible watching. Solar elongation, the angle between the comet and Sun from Earth's viewpoint, falls under 30 across much of this vital window. Picture attempting to catch a glow from a firefly right beside a blazing spotlight, and you'll grasp the spotting dilemma. Even top-tier scopes fail to tease out 3I Atlas's dim glow from our star's blinding blaze when they're bunched in the view. This inherent constraint of terrestrial observing implies the comet's liveliest phase might unfold mostly out of sight. The conjunction schedule weaves a stark paradox into the 3I Atlas saga. Precisely when sun-warmed peaks ignite and the comet might unleash its wildest shifts, Earth's skywatchers find themselves sightless. Prime venting, likely breakups, and fullest tail formation may all unfold in the span when surface scopes prove useless. This blind spot elevates the vital role of probes scattered across the system, especially Mars orbiters. The European Space Agency's Mars Express and Trace Gas Orbiter, plus NASA's Mars Reconnaissance Orbiter and MAVEN, now step up as our chief sentinels for one of the era's grandest celestial spectacles. Throughout the decade, the timeline following perihelion presents a balanced view of optimism and practicality regarding potential sightings by observers. If the 3I Atlas survives its close solar pass unscathed, terrestrial viewing could recommence in November or the start of December, once the sun's position allows for feasible angles. That said, the comet is expected to dim quickly afterward, having depleted a significant portion of its volatile materials amid the intense unseen heating phase at its peak. Forecasts indicate that, at its most luminous, 3I Atlas will still demand telescopes for detection from Earth. Estimates for maximum brilliance place it at around magnitude 11 to 12 too dim for unaided eyes, yet accessible via typical amateur astronomy gear. While the absence of a dazzling visible display might leave hobbyists underwhelmed, it in no way reduces the profound importance of this rare interstellar visitation for research. The speed dynamics highlight a key feature of the 3I Atlas schedule. As it nears perihelion, gravitational pull from the sun keeps boosting its velocity. Yet right after the nearest point, that influence shifts to slowing the comet down as it recedes from the sun. Such shifts in motion influence how long the height of heating lasts and the intervals when Mars-orbiting probes can gather data. Peering past perihelion, path projections depict 3I Atlas heading outward across the solar system, drawing near Jupiter by March 2026. Although this rendezvous happens far farther out than the Mars pass, it could yield extra chances for probe scrutiny as the comet embarks on its ultimate departure from our system. This schedule establishes a tight slot for unprecedented astronomical pursuits. In contrast to recurring comets that cycle back for repeated examinations, 3I Atlas grants just one shot to probe an artifact from a distant stellar realm. The hurdles of visibility, alignment with planetary positions, and mission timings all need to synchronize flawlessly if we're to glean the fullest insights from this stellar wanderer. With the pivotal October moments looming, the inquiry goes beyond what 3I Atlas might disclose about its nature. It's also about whether our detection tools can adequately seize those disclosures. Orbital calculations have fixed the agenda, and it demands prompt action from all involved. Part 4, Coma, Expansion and Structure. The most remarkable finding concerning 3I Atlas transcends its extraterrestrial roots or odd path. It's the vast, implausible expanse of the gaseous envelope enveloping it. Back in September 2025, NASA's Spitzer telescope spotted an anomaly that upended long-standing comet theories. A sprawling carbon dioxide halo reaching 348,000 kilometers from the core. To appreciate the scale, this ethereal shroud spans about half the width of our Sun. The 3I Atlas coma has ballooned to encompass Mercury's full orbital path, forming a vast sphere of gas and particles that overshadows any standard comet aura in our solar system. This goes beyond atypical. It's a milestone in comet studies. A coma emerges as sunlight warms the frosty nucleus, triggering sublimation, where ice is vaporized straight from solid to gas, bypassing liquid. Imagine a stellar ice ball fizzing under rays, yet this image understates the ferocity involved. When entrenched ices burst into vapor, they propel dust grains and bigger fragments outward, forging a swelling shell that can swell to immense sizes. The makeup of 3I Atlas's coma narrates origins in an environment starkly unlike our own solar setup. The prevalence of carbon dioxide ahead of water ice implies formation where CO2 solidified more easily than H2O, perhaps in the chilly fringes of another star's disk, cool enough for CO2 frost to persist, even as water lingered mostly gaseous. Such a CO2-heavy setting points to the elemental milieu at 3I Atlas's genesis. In our solar system's comets, water usually leads as the chief volatile, with CO2 in support. The flipped balance in 3I Atlas signals birth under thermal and pressure regimes alien to local bodies. Still, the coma's makeup isn't its sole quirk. Snapshots from the Hubble Space Telescope and Earth observatories unveil patterns that upend core ideas on comet dynamics. Rather than the usual tail-trailing anti-sunward, 3I Atlas exhibits what's termed an anti-tail, a stream of ejecta, seemingly aimed toward the sun. The sun-facing formation of this comet poses a riddle that has haunted scientists with endless investigations. Standard models of comet behavior predict that sunlight's force would drive gases and particles outward, away from the star, forming the classic tales that have fueled legends across generations. However, 3I Atlas appears to defy this fundamental rule, releasing substances in ways that challenge established theories. Images from Hubble on July 21st revealed what the team called a leading radiance, a wedge-like feature stretching from the core in the direction of the sun, not repelled by it. Subsequent photos from the Gemini South Observatory on August 27th indicated that this odd configuration endured and shifted, implying the countertail is an enduring trait, not just a fleeting oddity. The mechanisms driving such countertails go beyond basic photon push. Heavier dust particles, resistant to swift deflection by solar rays, can hold sun-oriented paths if launched from the core with enough starting speed. Moreover, optical illusions from our planet's viewpoint can cause matter traveling in 3D to look as if it's aiming sunward. Still, simulations fail to account for the durability and clarity of 3I Atlas's solar plume. It seems too sharp and persistent to stem from mere viewing angles alone, and the dust sizes plus launch speeds required for such an elaborate countertail strain the limits of comet core plausibility. Fresh studies propose the countertail arises from atypical spin patterns or distinct surface traits peculiar to visitors from beyond our system. A nucleus, rotating leisurely, might sustain varying heats between lit and dark hemispheres, directing vapor release along targeted paths. Or, the makeup of 3I Atlas's exterior could feature substances reacting to stellar warmth in manners alien to experts familiar with homegrown icy wanderers. The rate at which the coma spreads introduces further intrigue. Spectral data show gas speeds in the envelope surpassing norms for bodies at comparable solar distances. This boosted emission might arise from hypervolatile substances stable only in deep space, which vaporize quickly upon hitting stronger sunlight. Infrared scans of the coma uncover more irregularities in temperatures. The readings point to warming sources exceeding straightforward starlight capture. Candidates include reactions among once isolated chemicals or the unleashing of pent-up energy from bizarre ice formations born in interstellar voids. By piecing together the coma's 3D form from varied perspectives and light bands, experts detect imbalances hinting at uneven venting from the core's face. Unlike the balanced envelopes of familiar comets, 3 Atlas exhibits streams and sprays of ejecta bursting from particular zones on its heart. These streams indicate the core holds isolated patches of volatile latent stuff, perhaps bared by collisions or heat swings over its cosmic voyage. The venting layout might encode clues about the object's birthplace and changes over eons adrift in the void. Examining dust in the coma yield size spreads differing from those in system-native comets. The prevalence of big grains needed for the scene countertail hints that 3I Atlas either originated with altered dust-ice balances compared to locals or its particles evolved through interstellar processes. The spreading patterns display changes over time, linking to solar proximity and maybe spin cycles. As 3I Atlas nears its closest solar pass, the envelope keeps swelling and transforming, possibly ballooning further under ramped-up heating. Efforts to forecast its development encounter novel hurdles. The atypical makeup, countertail shape, and heightened emission levels demand tweaks to classic comet theories. Teams are crafting fresh conceptual tools on the fly as data exposes startling traits. The reach goes further than 3I Atlas alone. Should such exotic envelope traits prove common in interstellar wanderers, it implies our comet knowledge, drawn mostly from solar system residents, covers just a sliver of potential dynamics. Such an interstellar object might compel scientists to rethink core ideas about the origins and development of these celestial bodies. With 3I Atlas drawing nearer to its pivotal flybys of Mars and the Sun, the ongoing growth and shifts in the comet's coma will offer key opportunities to evaluate rival hypotheses. The big uncertainty is if the most intense alterations will happen amid the period when terrestrial observatories lose sight of the comet's activities. Yet the coma's development is just one facet of 3I Atlas's metamorphosis under our star's radiant influence. The standout visual shift took place around mid-September when the whole comet started emitting an otherworldly green radiance, hinting at chemical processes unseen before in any cosmic wanderer from beyond our system. Section 5. Hue alteration, that emerald sheen. Midway through September 2025, 3i Atlas sparked widespread intrigue among astronomers by shifting to green, not in a slow fade or faint hint, but in a brilliant jade luminescence that turned this distant intruder from a dim blur into a seemingly vibrant entity against the cosmic void. The hue switch didn't catch the eye of backyard stargazers right away. 3i Atlas is still too dim for unaided viewing, but advanced detectors on global scopes started snapping shots revealing a clear verdant aura around the core. The effect grew sharper in snaps from the September 14th lunar eclipse as the Earth's shadow dimmed the background, boosting the comet's fresh brilliance. This verdant shine narrates a tale rooted in quantum physics and atomic reactions. Specific compounds soak up solar UV rays, exciting their electrons to elevated levels. When those electrons drop back, they release photons at precise lengths, which we see as particular shades. For 3i Atlas, the teal output probably stems from C2, the paired carbon unit in chem terms. This diatomic form acts like a glowing cosmic billboard. Hit by the sun's UV, C2 releases rays near 5 or 16 nanometers, yielding the signature emerald that sets 3i Atlas apart as a strikingly photogenic comet lately. Known as fluorescence, this mechanism converts unseen sunlight into detectable beams, spanning vast distances to hit our ground scopes. The twist comes here. Preliminary spectral scans of 3i Atlas detected scant signs of carbon-rich stuff. First chem breakdowns pointed to a makeup heavy on CO2 and H2O, with minimal hints of the carbon compounds that usually cause green hues in comets. This clash between the seen glow and the detected makeup has experts racing to decode the dynamics in the comet's swelling envelope. A potential factor is changes in how the comet vents gases. As 3i Atlas neared the Sun and passed the 2 AU mark early that month, stronger heat could have vaporized hidden carbon stocks deep inside the core. These reserves, sealed during the eons-long trek through space, may now face sunlight for the first time. The green onset aligns oddly with the swift luminosity jump noted in mid-September, implying that the surge, perhaps from a sudden vent of buried volatiles, also sparked the reactions behind the teal light. Other theories for the tint swap draw on trickier reactions beyond basic C2 glow. Comets hold myriad carbon variants, each with unique light signatures. The seeming green could mix outputs from various types or stem from exotic carbon forms rare in local comets, but common in interstellar ones. Tech limits and data handling add fuzziness to hue assessments. Scopes with varied bands and processors yield slight color variances for the same target. One pic's pure green might veer cyan or lime in another, based on captured bands and how they're merged into full-color views. The progression of that verdant radiance offers additional insights into the fundamental chemistry emerged from this phenomenon. In contrast to the consistent glow anticipated from basic molecular fluorescence, the data indicate that the greenish hue fluctuates in brightness and spread across the coma, with certain areas displaying a stronger emerald tint than surrounding regions. This implies an uneven dispersal of carbon-containing compounds amid the dispersing gaseous envelope. Such irregularity in distribution may stem from targeted venting episodes, during which streams of substance burst forth from particular spots on the comet's core, transporting distinct chemical makeups. On the other hand, these differences could arise from ongoing reactions inside the coma, where sunlight's ultraviolet rays decompose intricate organic structures into basic components that emit light at varying frequencies. Moreover, the emerald radiance serves as a key indicator for assessing the environmental factors in the coma. The strength of this molecular fluorescence hinges on the concentration of the molecules, their thermal state, and the potency of incoming solar UV light. Through tracking variations in the emerald luminescence relative to the nucleus's distance and its temporal shifts, scientists can outline the spatial architecture of the carbon-rich vapor in 3i Atlas's envelope. Assessments of temperature based on the glow's properties reveal that these carbon molecules maintain a balanced heat equilibrium with the broader cometary gases. This points to effective exchange of energy among diverse molecular types, offering clues about interaction frequencies and fluid movements in the swelling atmosphere. The emergence of this verdant tint in 3I Atlas contributes yet another distinction to the expanding list of contrasts between extrasolar intruders and homegrown solar system bodies. 1I Oumuamua exhibited no evident cometary behavior and thus no shifts in coloration. 2I Borisov presented typical comet hues, primarily blue and white from reflected sunlight, without prominent molecular bands. 3I Atlas stands as the inaugural interstellar comet to exhibit the iconic green envelope that hobbyist stargazers link with inbound short-period comets. That said, the precise spectral lines and vigor of this green output might subtly diverge from those in well-known comets, possibly unveiling molecular profiles distinctive to entities born around distant suns. The onset of this color shift heightens the need for prompt observations. With 3I Atlas nearing superior conjunction and fading from terrestrial view by early October, the luminescence could persist in transformation or diminish altogether. The maximum fluorescence intensity typically peaks around perihelion, when solar warmth intensifies to its height. Yet this pivotal phase will mostly elude ground-based scopes. Follow-up spectral analysis seek to pinpoint the exact compounds fueling the green light. However, securing such data demands expansive instruments and optimal viewing windows, which grow scarcer as the comet nears the solar blaze. Every clear evening turns vital as observers hurry to profile the glow before the object slips from view. Beyond its captivating visual appeal, the shift to an emerald aura offers concrete proof that 3I Atlas is experiencing profound chemical alterations under our sun's influence. The entities now radiating in the cometary haze probably stayed dormant chemically for eons, locked in icy stasis throughout their transit across interstellar voids. For the initial time post-formation, 3I Atlas is igniting vividly as stellar rays trigger long-slumbering reactions from its origins near a foreign star. This verdant illumination signals the revival of extraterrestrial reactions, the initial activations of molecular processes in substances shaped in environments potentially alien to our own system. Yet, capturing this revival strains the boundaries of terrestrial observing techniques. These hurdles will compel investigators to turn to automated sentinels scattered across the solar domain for ongoing surveillance of our evolving cosmic guest. Section 6. Hurdles in Viewing. The cosmos displays an ironic timing regarding 3I Atlas. Precisely when this extrasolar wanderer starts unveiling its most captivating mysteries, the swift illumination, the ethereal envelope, the otherworldly emerald sheen. The dictates of celestial mechanics align to conceal it from earthly gazes at the journey's decisive juncture. Even elite professional scopes, armed with cutting-edge technology, confront the identical core constraint that bedevils casual skywatchers: invisibility behind the sun's disk. As 3I Atlas presses onward to perihelion, its celestial placement inexorably draws nearer. The intense brilliance of nearby stars poses formidable barriers to observing celestial bodies, hurdles that even cutting-edge technology struggles to surmount. On August 6th, the James Webb Space Telescope succeeded in obtaining spectroscopic data from 3I Atlas via its near-infrared spectrograph, yielding vital insights into the object's chemical makeup during a rare period when the premier orbital facility could aim at the comet without endangering its components from solar exposure. Such data marks among the finest chemical breakdowns available for an extrasolar visitor. Yet, it predates the striking shifts in mid-September that turned 3I Atlas from an oddity into a true enigma. The Hubble Space Telescope added its input on July 21st, delivering sharp images that highlighted the tail's orientation toward the sun and offered estimates for the core's dimensions. That said, detailed views from leading orbital platforms have grown scarce since August. The very instruments equipped to dissect 3I Atlas's peculiar traits are also the most susceptible to sunlight disruption as the comet nears its solar alignment. Earthbound facilities grapple with a series of hurdles too. Telescopes employing varied filters and calibration methods often yield conflicting luminosity readings. Such discrepancies are commonplace in the field. Assessing brightness or photometry demands meticulous handling of weather factors, device tuning, and uniform protocols that differ across sites. Efforts like the Comet Observation Database work to harmonize these variations by aggregating global reports on magnitude and comparing them to simulations. In September, the compiled figures plainly indicated 3i Atlas outshining forecasts, with actual values steadily surpassing the projected line. Still, the variability in those readings underscores the difficulties for those monitoring a swiftly evolving target that upends established predictions. Hobbyists, relying on modest scopes and basic gear, supply essential ongoing records that big league setups sometimes overlook. Yet their data carries extra risks from air distortions, urban glow, and tool constraints. Together, this mosaic of inputs sketches an image of anomalous activity, even as each piece harbors ambiguities that spark arguments over the true nature of events. Platforms like The Sky Live and similar trackers merge these inputs into brightness profiles, charting changes across time. Resources monitoring through. Atlas uniformly display the concerning pattern, observed intensities rising beyond expectations, especially post-mid-September. Nevertheless, the exact scale of this outlier stays murky, given the tricks of gauging dim, fast-altering targets. The key limiter is solar elongation, the apparent angle between 3i Atlas and the Sun from our vantage, which caps all viewing efforts. When it shrinks under 30 degrees, top-tier instruments falter in distinguishing the comet's glow from atmospheric sun scatter. Experts usually halt tracking below 20 degrees of separation, whereas backyard stargazers might drop it sooner amid gear shortcomings and site-specific issues. This angular schedule sets an unyielding timer beyond tech's reach. Come early October, 30 Atlas slips beneath the 30-degree mark, signaling major viewing woes. By mid-October, it falls under 20 degrees, halting standard ground watches. This blackout lasts into early November, covering the peak of solar warming. The contradiction stings. It's like straining to spot a dim interstellar sparkler beside a blinding beacon with tools built for catching galaxy-edge flickers from eons away. Even tech like adaptive optics, which counters air wobbles, or coronagraphs that mask starshine, falters against the core rules of sunlight diffusion when the comet hugs the sun's sky position too tightly. Orbital labs, in principle, hold edges over surface arrays against sun glare, yet they confront parallel limits. Gear on Hubble and James Webb features safeguards that bar unsafe sunward tilts, triggering auto-pauses at risky angles. These protective mechanisms, vital for averting severe harm to expensive observatory equipment worth billions. This alignment generates critical blind spots exactly during the moments of greatest scientific interest. The alignment of the 3i Atlas with the Sun couldn't come at a more unfortunate time for probing its height of activity. Models suggest that the strongest gas emissions, potential breakups, and the most striking tail formation are all likely to happen around perihelion toward the end of October. These very features hold the key to unlocking insights into the makeup, build, and history of 3i Atlas, yet they'll unfold mostly out of sight from earthly viewers. The hurdles in handling data only worsen these viewing problems. Pictures of 3i Atlas demand meticulous refinement to isolate the comet's glow from stellar backgrounds, radiation from space, and device glitches. As the body dims against the increasing glare of the sky while nearing conjunction, such refinements grow ever more vital and more likely to spawn inaccuracies or false signals. Spectral studies crucial for decoding the makeup of gases in the comet's envelope, and tail call for even more precise setups than basic light readings. The tools that split comet radiance into spectral bands perform optimally on vivid objects viewed against night skies. With 3i Atlas dimming amid the sun's brilliance, chances for in-depth spectral scrutiny disappear right as chemical reactions might intensify. Earth's air impacts various light colors unequally. UV rays, essential for spotting numerous gas types in comet hazes, prove especially tough to detect as the angle from the sun shrinks, since our atmosphere disperses short blue and UV waves more than longer red ones. This dispersion, responsible for the sky's azure hue, poses extra obstacles to examining the reactions in 3I Atlas's swelling gaseous shell. Linking efforts across global sites turns indispensable as viewing quality declines. Sites at varied latitudes and hours must collaborate to exploit the slim nightly slots for observation. Outposts in the southern skies could hold on to favorable angles a bit longer than northern ones, opening doors for prolonged tracking that hinges on tight worldwide teamwork. The fluctuations seen in light readings go beyond tool shortcomings. They might signal actual shifts in 3I Atlas's emissions. Comets often experience quick brightness swings from gas bursts, spinning influences, or alterations in their cores. Telling apart observational fuzz from true comet changes gets harder as the clarity of signals drops heading into conjunction. Ground viewing faces yet another wild card: the weather. Overcast skies, air distortions, and typical seasonal storms at key sites can wipe out vital viewing sessions that won't come back. Unlike repeating comets with regular returns, 3I Atlas grants just one trip close to the sun, rendering every clear evening invaluable and unrepeatable. The difficulties stretch past single sessions to the larger issue of making sense of whatever data we gather. The light pattern indicating 3I Atlas surpassing forecasts might point to boosted emissions, core shifts, or mere flaws in the prediction frameworks. Answering this demands the sort of thorough, ongoing surveillance that vanishes as the comet slips behind solar light. As terrestrial stargazing hits its barriers with 3I Atlas, the duty for ongoing watch passes to robotic sentinels scattered across the solar realm. Probes circling Mars, built for unrelated tasks, now step up as humankind's main watchers of one of the era's standout celestial happenings. Section 7. The mounting concern in the astronomical world. Beneath the precise wording of research articles and the tempered remarks in observatory updates, a wave of thrill and indeed worry sweeps through comet specialists everywhere. 3I Atlas defies the long-established patterns of comet studies, and experts are starting to concede, in their guarded scientific fashion, the chance of observing an event without precedent. The light curve tracked by watchers across the globe signifies far more than random fluctuations or tracking glitches. Diverse autonomous monitoring setups, from central comet archives to dedicated hobbyist groups, reveal the identical disturbing trend. 3I Atlas steadily outshining. Forecasts from conventional cometary simulations, the extent of this discrepancy spanning multiple magnitudes beyond anticipated brightness, lies far beyond the usual bounds of measurement errors. In a recent discussion, Dr. Matthew Knight, a lifelong expert in cometary dynamics, highlighted how the swift luminosity surge spotted in mid-September upends core ideas about the release of volatile materials in these celestial bodies. He pointed out that the pace of this shift points to mechanisms unfolding on timescales far quicker than those assumed in the slow-warming frameworks often employed to forecast comet activity. Such unknowns spark a unique thrill within the scientific circle, as experts confront the prospect of witnessing events that could necessitate entirely fresh conceptual models to interpret. Coverage in Earth's skies outlets captures this interplay, detailing sightings that keep astonishing specialists, even as they concede that many oddities may stem from the intrinsic volatility of wanderers born in distant stellar realms. The forward-jutting plume configuration sparks its own wave of scholarly intrigue. While anti-tails aren't unheard of in cometary studies, the endurance and vividness of 3I Atlas's sun-facing jets stretch current theories to their limits. Scientists are now floating more unconventional hypotheses, such as atypical dust particle makeup, irregular core spinning, or rare volatile blends, to make sense of conduct that bucks standard doctrines. A consensus among specialists holds that 3I Atlas displays heightened vigor relative to ordinary comets at comparable solar distances. The CO2 heavy envelope, as picked up by SphereX and stretching to remarkable extents, implies release rates that surpass baseline estimates by wide margins. This marks no minor divergence from established norms. Rather, it's a striking break that calls for rigorous accounting. Still, the research world contends with the concept of outburst bias, the inclination of comets to experience short bursts of amplified output, fostering misleading views of ongoing anomalies. These icy visitors are well known for abrupt spikes in brilliance, often chased by swift drops back to norm. Lingering over 3I Atlas's sightings is whether the September flare signals a true break from routine or just a fleeting spike destined to dim just as abruptly. This ambiguity grows more acute amid the looming blackout in observations. The pivotal window for decoding 3I Atlas's essence, the fragile span around perihelion when sunlight's warmth peaks, will unfold mostly veiled from terrestrial scopes. Should the comet unleash its boldest shifts, then, investigators might forever puzzle over the September spectacle. Dr. Carrie Halt, an interstellar object specialist at the European Southern Observatory, voiced the widespread irritation among peers. The precise instant when 3I Atlas could unveil its deepest mysteries aligns with when ground-based viewing hits its lowest ebb. She dubbed this alignment a celestial plot thwarting insight. Discussions reach past mere light readings to core inquiries about 3I Atlas's makeup as a material entity. Spectral breakdowns reveal CO2 to water ratios diverging sharply from those in homegrown solar system comets, potentially signaling origins vastly unlike our cosmic neighborhood. Alternatively, it could trace to alterations from eons cruising through interstellar voids. Hobbyists in astronomy have emerged as vital allies in tracking 3I Atlas, delivering steady data streams that pro-facilities can't always sustain. Yet, the fragmented quality of these enthusiast readings brings fresh hurdles. Varied setups and methods among observers can yield brightness figures clashing by notable degrees, complicating efforts to discern true comet shifts from instrumental quirks. The European Space A's monitoring, run via their Space Awareness Initiative, works to harmonize these inconsistencies while keeping tabs on 3I Atlas's path and light progression. Their review upholds the overall pattern of boosted radiance, but concedes the challenges in pinning down the precise degree by which the comet outpaces model forecasts. Social platforms in the astronomy world show a blend of eager scientific interest and measured professional restraint in reacting to 3I Atlas. Scientists post initial photos and luminosity data, all while highlighting the doubts and constraints in their findings. Their wording indicates a clear understanding that they're witnessing something possibly groundbreaking, yet they stay cautiously reserved against jumping to early judgments. The shift to green hues recorded around mid-September heightens the mystery in this scientific puzzle. Although emissions from diatomic carbon could account for the seen tint, the moment and strength of that emerald shine don't fully align with the makeup revealed by prior spectral analyses. This mismatch between the chemical readings experts obtain and the sights they witness points to either flaws in detection methods or reactions far more intricate than typical theories anticipate. Talks lined up at the American Astronomical Society's Division for Planetary Sciences conference cover various sessions on 3I Atlas sightings and simulation work. The summaries show teams across the globe striving to grasp not only the actions of this object, but also the reasons why standard frameworks fall short in forecasting its patterns. The pressing drive felt by these experts goes beyond mere inquisitiveness in science. It stems from the acknowledgement that chances to examine interstellar wanderers are incredibly scarce. Having just 3 verified such intruders in recorded history, everyone delivers priceless insights into environments around distant suns and the mechanisms shaping minor celestial bodies across the cosmos. Global teamwork has ramped up as the chance for viewing shrinks. Observatories in Chile, Hawaii, the Canary Islands, and Australia synchronize their efforts to ensure broad surveillance, while 3I Atlas heads toward the solar conjunction phase that will halt everyday ground observations from Earth. Every site brings distinct strengths, from detailed imaging setups to tailored spectral tools, aiming to pull the most knowledge from the leftover viewing slots. Meanwhile, the expert astronomers face hurdles in sharing info with the public about 3I Atlas. News coverage at times exaggerates the sureness of research outcomes or dramatizes traits of the comet's actions that the scientists themselves flag as tentative. Juggling widespread fascination with this uncommon space traveler against the built-in ambiguities of active studies demands precise handling of result disclosures and understandings. Frameworks for evaluating threats from possible risky asteroids are getting fresh scrutiny regarding 3I Atlas. Not due to any risk it presents to our planet, but because its erratic ways underscore gaps in today's grasp of how tiny objects react to sun warmth. Should experts struggle to foresee the moves of 3I Atlas, it raises doubts about the trustworthiness of systems applied to gauge dangers from additional items. The growing buzz over 3I Atlas captures a core truth of scientific breakthroughs. It's the awareness that the universe keeps yielding events more elaborate and unexpected than our concepts can foresee. With October drawing near and Earth views turning tougher, stargazers are pinning hopes on probes scattered in the solar system to snag the insights that surface telescopes must forgo. The Mars Pass in Part A offers a prime chance. As our planet gears up to have its view of 3I Atlas washed out by solar brightness, a different planet readies for prime viewing of one of the biggest sky spectacles lately. Come October 3, 2025, Mars will stage our species' nearest brush with an interstellar guest, granting orbiters around the rusty world unmatched chances to scrutinize 3I Atlas from a spot ground scope's envy. The setup is ideally timed. While 3I Atlas glides by Mars at about 30 million kilometers away around Arshro, 2 astronomical units, several active probes in Martian paths can aim their gear at this stellar drifter. This lines up right before superior conjunction blocks Earth tracking, forming a vital relay from planet-bound to orbital watch. The European Space Agency's Mars Express, sent up in 2003 and operating well past its planned span, features the high-resolution stereo camera that has charted Mars's landscape with remarkable clarity for more than 20 years. Though built for surface studies, the HRSC holds the finesse and responsiveness to a promising approach could involve using Mars orbiters to obtain high-detail photographs of 3I Atlas's core and the inner layers of its dust envelope. Dr. Colin Wilson, the lead scientist on the ESA Mars Trace Gas Orbiter project, has stated that the mission team is assessing possibilities for the CASIS color and stereo surface imaging instrument, as well as the Nomad Nadir and occultation for Mars Discovery Spectrometer to target the interstellar object. These devices, intended for examining the makeup of Mars's atmosphere and its terrain characteristics, may succeed in identifying molecular traces inside 3I Atlas's broadening coma. The NASA Mars Reconnaissance Orbiter offers some of the most compelling options for in-depth study. Its high-resolution imaging science experiment, HiRISE, regularly records ground features under 1 meter in size from an orbit about 300 kilometers over the planet's surface. Although 3I Atlas will zip by at a greater distance, HiRISE's exceptional clarity could uncover aspects of the comet's central body that ground telescopes on Earth can't detect. Similarly, the MAVEN probe, part of NASA's Mars Atmosphere and Volatile Evolution mission, includes spectroscopic tools tailored to probe air chemistry and movements. Such features might help investigate the makeup of 3I Atlas's coma, especially the dominant carbon dioxide-laden vapors that define its spectral profile. That said, these viewing windows bring major engineering hurdles. Every Mars satellite was engineered and fine-tuned to focus on the planet, not to pursue rapid objects set against the stars. The attitude control mechanisms, crafted for tracking a massive close-up world, now need adjustments to track a tiny, far-off body traveling at cosmic speeds. The primary barrier lies in signal intensity. Even during its nearest pass by Mars, 3I Atlas will seem very dim to sensors built for planetary work, not outer space pursuits. With an anticipated brightness of magnitude 12 to 14, even as it flares up, it tests the boundaries of detection for the imaging and spectral gear on most Mars craft. In updates to the Global Astronomy Network, Dr. Wilson highlighted these constraints, explaining that although views from Mars of 3I Atlas are feasible in principle, the real value hinges on variables like the object's glow at perihelion, weather patterns around Mars, and the precise alignments needed for accurate aiming. Beyond mere nearness, observations from Mars hold broader benefits. The angle of view from the planet on October 3rd offers a vantage on 3I Atlas impossible from our homeworld. The phase angles formed by the Sun, the comet, and the watcher vary greatly between Mars and Earth positions, which could expose elements of the dust envelope and tail shape obscured from Earth observatories. Interactions with the solar wind offer yet another domain where Mars satellites could deliver distinct insights. As 3I Atlas meets the solar wind's flow of ionized particles from the Sun, it might generate effects picked up by the particle and field sensors aboard various Mars probes. Such encounters could disclose details on the comet's makeup and build through shifts in its electromagnetic traits. The ESA's efforts to synchronize Mars flyby studies mark a rare collaboration across missions with wholly separate goals. Mars Express, set up for land mapping and air research, is shifting to serve as a watcher of extrasolar bodies. The Trace Gas Orbiter, aimed at spotting methane and air reactions, has to tweak its setup for comet analysis. Scheduling pressures further complicate the planning. These orbiters stick to fixed timetables for standard planet scans, Earth link-ups, and upkeep routines. Fitting in sessions for 3I Atlas demands precise juggling to sidestep clashes with core tasks, yet sees the best chances for discovery. Sending the data back poses big issues too. Mars craft link to Earth only in set slots when planetary paths align for solid radio signals. Recordings and analyses of 3I Atlas will vie with everyday planet data for scarce transmission capacity, which might hold up public access to findings for weeks or even months. Backing these orbital efforts from the ground calls for teamwork among numerous agencies and labs across the globe. The European Space Operations Center in Germany, NASA's Jet Propulsion Laboratory in California, along with various other sites, needs to collaborate on designing viewing schedules, handling data streams, and sharing findings with scientists worldwide. Observations from Mars could dramatically advance our knowledge of Comet 3I Atlas in 3 key areas. Detailed imagery could pinpoint the comet's core dimensions and form with remarkable accuracy, resolving ongoing arguments over its physical makeup and build. Spectral analysis might uncover molecular components undetectable by Earth telescopes, uncovering chemical clues about the environment where the comet originated. Features of the surrounding gas cloud and tail, especially the bizarre plume extending toward the Sun that has stumped experts, could sharpen into focus from Mars's distinctive vantage point. The altered angle relative to the Sun might clarify if the backward-pointing tail stems from actual material shooting sunward, or is merely an optical illusion that shifts appearance depending on the observer's position. It's essential to temper hopes for what Mars spacecraft can deliver. Even in ideal circumstances, the gains from these views will probably amount to just a few snapshots and spectral readings, not ongoing surveillance efforts. These tools weren't built for such tasks, and their limits may fall short of unraveling core mysteries about 3I Atlas's essence and actions. Outcomes hinge on factors outside our grasp. Should 3I Atlas experience another surge in brightness before October 3rd, it could enter the detection range of Mars instruments that might otherwise deem it too dim to capture. On the flip side, if the comet dims from its present heightened glow, the most promising viewing plans could produce nothing worthwhile. The close pass by Mars stands as our prime chance to track 3I Atlas through the vital period when ground telescopes on Earth can no longer spot this visitor from beyond our system. While Earth-based stargazing braces for a forced blackout until early November, the robotic sentinels circling the red planet provide the sole prospect of catching what could turn out to be the comet's most spectacular stage in our solar system's embrace. No matter if these efforts triumph or falter, they signal a fresh era in humanity's pursuit of interstellar travelers, showcasing our advancing skill in syncing observations across planets, even as these targets whip by at cosmic speeds. Part 9. Superior Conjunction and Vanishing Act. The equations of orbital dynamics show no regard for our thirst for knowledge. As October advances and 3I Atlas presses on toward the Sun without pause, the unyielding geometry of paths aligns to whisk our cosmic guest from view right when it stands to disclose its deepest enigmas. Superior Conjunction, the stretch when 3I Atlas aligns too near the Sun in our heavens for feasible viewing turns, one of astronomy's landmark happenings into a stellar sleight of hand. The schedule plays out with ruthless exactness. Early in October, 3I Atlas slips under 30 of separation from the Sun. That's the point where major hurdles kick in for Earth telescopes. Sunlight diffused through the atmosphere lights up the sky, drowning out the comet's subtle glow. Top-tier observatories, equipped with advanced optics adjustments and vast light collection abilities, can push observations a bit further than hobbyist setups. Yet, even they confront mounting impossibilities. By mid-October, the separation shrinks below 20, shutting down regular Earth surface monitoring. The comet doesn't vanish in a flash. It dims steadily amid the Sun's blaze, much like a dawn star, growing tougher to spot until detection turns from tough to unattainable. This slow shift complicates nailing down the exact moment Earth bids farewell to 3I Atlas. Still, the outcome stays unchanged. Just as the comet's solar warming hits its height, our main view of its antics snaps shut. The conjunction spans into early November, covering about 4 to 5 weeks during which 3I Atlas stays practically unseen from our planet. This goes beyond a mere observational hiccup. It means total blackout on tracking the comet amid predictions of its peak frenzy. Intense gas release, full tail expansion, potential breakups, and other striking occurrences might all unfold out of our sight. The harsh twist sharpens in light of 3I Atlas's recent. The comet's activity hints at profound alterations triggered by exposure to solar energy. The swift surge in brightness during September, coupled with the peculiar backward-pointing tail and its striking emerald hue, all point to an entity experiencing core shifts under the Sun's intense rays. Reason suggests these shifts will grow more pronounced with escalating solar warmth, possibly culminating in dazzling displays as it nears its closest solar approach in late October. Unfortunately, this perihelion timing aligns precisely with the heart of the conjunction phase, when 3I Atlas seems nearest to the Sun from our planet's perspective, rendering direct viewing exceedingly difficult. No schedule could prove more inconvenient for unraveling how this cosmic wanderer transforms under peak solar exposure. It feels as though the cosmos has intentionally veiled the climax of the spectacle. The mechanics of superior conjunction harbor no plot against research. They stem simply from the orbital geometry of watching from a world that circles the same star as our subject. As 3 Atlas hurtles toward perihelion, its sky position inevitably draws nearer to the Sun's. This gradual narrowing of angular distance persists until the comet seems to slip behind the Sun, imposing viewing hurdles that even cutting-edge tools cannot surmount. Experts in astronomy grapple with such barriers routinely when examining sun-grazing bodies. Instruments on sun-watching probes like the Solar and Heliospheric Observatory, SOHO, occasionally capture comets amid conjunctions via coronagraphs that mask the Sun's glare. That said, 3 Atlas's path stays too distant from the Sun beyond just a handful of solar radii for these devices to detect it. This observational blackout poses novel hurdles for researchers habituated to steady surveillance tools. Contemporary celestial studies depend on prolonged tracking efforts that follow targets across full activity phases. For comets especially, ongoing scrutiny is essential to separate fleeting surges from enduring behavioral shifts. The unavoidable break in viewing during 3IA Atlas's pivotal phase dashes hopes for thorough evaluation. Probes scattered across the solar system present partial workarounds to terrestrial viewing limits, yet their functions are bounded by missions geared toward planet exploration over comet pursuits. The Mars-based spacecraft mentioned previously hold the best short-term prospects, though their glimpses will amount to fleeting captures instead of the sustained oversight required to grasp 3I Atlas's development. The European Space Agency's Bepi Colombo, en route to Mercury, pursues a path that could yield sporadic sightings of 3I Atlas from an alternate angle relative to Earth. Still, its gear prioritizes Mercury investigations, and the setup for comet viewing might clash with operational priorities. NASA's Parker Solar Probe, built to probe the Sun's outer atmosphere and particle flows, maneuvers in the Sun's inner domain, where it could, in principle, brush against 3I Atlas's tail gases or dusty envelope. Nevertheless, the probe's looping path and emphasis on solar dynamics rather than comet specifics curtail its value for dedicated tracking. This conjunction window also hampers computational forecasts, aiming to anticipate 3I atlases' responses. Models of comet dynamics draw on real-time sightings to fine-tune projections and confirm reliability. The 4 to 5 week void in data strips away vital inputs that experts use to sharpen insights into the interloper's reaction to solar heat. By the time ground observers can resume in November or December's dawn, 3I Atlas will almost certainly have morphed beyond recognition from its September form. It could shine even more vividly, perhaps sprouting elaborate tail features detectable by backyard scopes. On the flip side, depletion of icy components during the unseen solar skim might dim it sharply. In a bolder scenario, 3I Atlas could splinter apart at its sunward extreme. Such breakups happen frequently near perihelion as gravitational pulls and heat-induced strains overpower the fragile bonds in the core. Should splitting occur hidden by conjunction, terrestrial watchers will confront the tough job of spotting and following scattered fragments once visibility returns. Reviving observations in late November or December demands meticulous coordination, and coordination between global observatories plays a crucial role. Next, 3I Atlas will exit its conjunction in a new part of the sky, forcing telescopes to search and rediscover the comet following weeks of obscurity. The comet's luminosity, location, and visual features could alter enough to hinder recognition and monitoring. Public fascination with 3I Atlas encounters its share of conjunction-induced hurdles. News reports on celestial phenomena usually depend on striking visuals and ongoing reports to hold viewers' interest. The quiet phase amid conjunction cuts off the regular flow of fresh sightings that keep public curiosity alive, which might dampen enthusiasm right when the comet undergoes its most profound shifts. Learning prospects also take a hit during this observational void. Classrooms and hobbyist astronomy clubs frequently leverage vivid comets to instruct on solar system mechanics and viewing methods. 3I Atlases fade into the sun's blinding light strips away these teachable moments at a time when tail growth and core outbursts could offer the most captivating visual lessons. This conjunction interval highlights astronomy's inherent boundaries even after hundreds of years of tech progress. Observers are still tethered to Earth for the bulk of skywatching, vulnerable to the spatial restrictions dictated by our planet's stance against target bodies in the sun. Even advanced orbiting scopes can't fully surmount these barriers when targets draw near our star's spot. As 3I Atlas slips into solar dazzle, astronomers gear up for a stretch of guesswork and computer simulations drawn from partial info. The issue isn't if the comet will evolve in its concealed trek. Rather, will those evolutions make sense upon resumed viewing, or will the conjunction break spawn lasting enigmas about the key stage of this star-crossing guest's brush with our sun's path? Part 10. Anticipations for perihelion. Buried in the overwhelming solar blaze that shields Earth's instruments, 3I Atlas gears up for its fateful rendezvous. During October 29th to 30th, 2025, this cosmic drifter will hit perihelion, coming nearest to the Sun at about 1.36 to 1.4 astronomical units. Concealed from earthly eyes, the comet will face solar energy levels unseen in its multi-million-year trek among stars, possibly sparking alterations that reshape our grasp of such interstellar travelers. Just the velocity buildup hints at stellar ferocity. Now, hurtling at dozens of kilometers per second, 3I Atlas will peak in speed around perihelion, possibly reaching 68 kilometers or roughly 152 centimeters. To grasp this astonishing pace, note that Earth circles the Sun steadily at about 30 kilometers. 3I Atlas will outpace our world by over double, hauling momentum gathered on its grand galactic voyage. Science foresees perihelion igniting the climax of 3I Atlas's solar system brush. With solar warmth at its peak, the comet's core heat will climb, likely stirring dormant volatiles that stayed inert across its star-hopping path. Frozen water, CO2, CO, and rarer iced vapors might all vaporize at once, sparking a burst in the coma that could eclipse the vast spread seen in September. Heightened gas release might spawn dazzling dust streams bursting from specific spots on the core's face. Such streams, born when buried volatiles break free via channels, can form geyser-like formations stretching thousands of kilometers outward. The enigmatic sun-facing anti-tail that's baffled watchers could surge wildly, or fresh tail forms might arise as varied volatiles join the coma mix for the first time. Simulations indicate 3I Atlas's CO2-heavy makeup could yield perihelion antics distinct from usual inter-system comets. CO2 turns to gas easier than water ice under expected perihelion heats, possibly yielding gas outputs that outstrip water-led comets by notable margins. Such boosted vigor might show as swift shifts in glow, coma extent, and tail shape, unfolding in hours instead of the days or weeks common in comet progression. The risk of breakup overshadows perihelion forecasts like an ominous veil. Comets stand as among the most cometary nuclei, represent some of the most delicate bodies in the solar system, bound by feeble gravity and the cohesion of their frozen cores. Extreme solar warmth generates heat strains that, alongside the physical pressures from violent gas releases, can overpower these cohesive bonds and shatter the cores. Such breakup incidents often occur with startling abruptness. Even a comet seeming solid as it nears its closest solar point might fracture into several fragments in mere hours, triggered by temperature differences causing material flaws or bursts of gas pressure that dig into the core's depths. Should 3I Atlas undergo such splitting, ground-based watchers will encounter the challenge of spotting and following numerous fragments once viewing restarts in November. Past instances of cometary breakup close to perihelion feature striking cases, such as Shoemaker-Levy 9, which fragmented due to Jupiter's gravitational pull prior to colliding with the giant world in 1994. In more contemporary times, a comet fully broke up amid its perilously tight solar pass in 2013, forming a swiftly scattering rubble trail as it receded from perihelion. That said, splitting is not a guaranteed outcome. The durability of 3I Atlas hinges on elements like core makeup, inner porosity levels, spin speed, and the precise heat loads from its distinctive mix of ices. Bodies from beyond our solar system could exhibit build qualities markedly unlike those of local comets, perhaps rendering them either tougher or more vulnerable to heat-induced breakdown. The pace at which 3I Atlas hurtles through perihelion also affects the odds of disintegration. In contrast to comets that hover longer near their solar minimum, 3I Atlas will zip by swiftly thanks to its hyperbolic path. This brisk transit shortens the time of maximum warmth exposure, which might lessen the overall heat burden on the core. Assuming 3I Atlas emerges from perihelion whole, the phase afterward could showcase a body altered by its brush with fierce solar rays. The surrounding gas envelope may swell to vast sizes as maximum outgassing scatters substances over immense spatial regions. Fresh molecular types, freed from buried layers by profound warming, might show up in spectral data for the initial time. Shifts in hue, extending past the noted green glow, could arise as varied molecules start glowing under the sun's UV light. If intricate organics lurk in the core, they may decompose into basic pieces that shine at signature wavelengths, possibly yielding a spectrum of colors in visible light. The backward-pointing tail feature seen in 3I Atlas sightings could transform strikingly around perihelion. Boosted dust ejection might form various tail formations aimed variably, since grains of differing scales react uniquely to solar radiation push. This setup could yield vital details on the core's turning speed, outer makeup, and inner build. Studying dust particles gains special relevance around perihelion. The range of sizes and makeup of expelled bits mirrors the core's inner layout and birth environment. Bigger particles may signal a crumbly core riddled with empty pockets, whereas tiny dust hints at a denser build or chemistries that promote fine particle creation. The electromagnetic and charged particle surroundings near perihelion introduce further intricacies to 3I Atlas's actions. Solar wind ions flowing from the sun mingle with charged gases in the envelope, sparking intricate electrical effects. Such exchanges can speed up bits to extreme speeds, produce bright shimmers in the envelope, and shape ion tails stretching millions of kilometers from the core. Heat readings at perihelion, if captured by probes, might offer key revelations about 3I Atlas's warmth traits and inner design. Specific ices turn to gas at set heat levels, acting as a gauge of warming stages. Solar energy seeps into the core's outer shells. What follows perihelion will rely heavily on the volume of ices in 3I Atlas and how well they vent from the core's exterior. Bodies rich in ices could sustain heightened outbursts for weeks or months post-perihelion, whereas ones low on volatiles might dim swiftly as their outer coatings wear thin. Solar gravity's strong tugs could then, the gravitational influence close to perihelion, might likewise influence the upcoming path of 3IE Atlas. Although the comet is certain to proceed along its hyperbolic orbit away from the Sun, minor shifts in speed could modify the schedule and configuration of subsequent interactions with distant planets in the outer solar system, especially Jupiter in 2026. Passing through perihelion marks the peak of 3IE Atlas's journey through our solar system. This is the instant when eons of interstellar development collide with the fierce radiation zone around our star. Regardless of whether this collision sparks dazzling bursts of celestial fireworks or subtle internal modifications concealed in an enlarging coma, the perihelion event will irreversibly transform 3IE Atlas from the entity that first arrived in our solar system into an entirely novel and unparalleled form. Astronomers will grapple with one key question during the conjunction phase. Will 3IE Atlas reappear after its obscured perihelion transit, still identifiable as the same captivating body that drew observers in September? Or will it have undergone a profound metamorphosis due to exposure to the Sun's harshest radiation? The solution remains concealed amid the solar brightness, pending the deliberate alignment of orbital dynamics to disclose the effects of perihelion. Part 11. Parallels with earlier interstellar intruders. To grasp the importance of 3IE Atlas and its odd conduct, we need to review the short yet transformative record of verified visitors from beyond our solar system. Just 2 prior objects to our current guest have been conclusively confirmed as extrasolar in origin, and each has reshaped astronomical knowledge in its distinctive manner. Collectively, their narratives highlight a vast array of cosmic variety, upending traditional ideas about the behavior of these nomadic envoys from distant stellar realms. The first, 1I Oumuamua, was spotted on October 19, 2017 by the Pan-STARRS telescope in Hawaii through the Panoramic Survey Telescope and Rapid Response System. At first deemed an asteroid for its absence of a visible coma, Oumuamua soon demonstrated that interstellar wanderers defy predictions rooted in our earthly observations. Its extreme cigar-like form, approximately 400 meters in length and 40 meters across, bore no resemblance to any known asteroid or comet within our solar system. Even more baffling, Oumuamua displayed anomalous non-gravitational propulsion as it receded from the Sun, accelerating in manners not attributable solely to gravity. This enigmatic boost ignited ongoing controversies. Could it stem from subtle venting of concealed icy materials, the push of solar radiation on its peculiar contours, or perhaps an unconventional phenomenon testing the limits of established physics? The lack of a noticeable coma around Oumuamua clashed with predictions for bodies harboring the volatile ices common in comets. Nevertheless, an unseen influence evidently propelled the object to yield the detected speedup. The explanation, such as it is, relies on trace outgassing too faint for detection, yet potent enough to tweak Oumuamua's course. The second, 2I Borisov, was found on August 30, 2019, by hobbyist Gennady Borisov in Crimea, offering a starkly contrasting character. In contrast to the puzzle of its forerunner, Borisov initially seemed straightforwardly conventional. It behaved like a textbook comet, featuring a hazy coma and evolving tail features that aligned with models for sun-warmed bodies. Yet, closer scrutiny exposed that Borisov's seeming familiarity concealed chemical makeups divergent from those in our solar system's comets. Spectral data indicated carbon monoxide levels far exceeding norms for indigenous comets, pointing to origins in a protoplanetary disk with distinct thermal and chemical profiles compared to our solar nebula. The dust-to-gas proportions in Borisov's coma also deviated from local standards, hinting at alternative birth mechanisms or alterations accrued over its interstellar voyage. Such understated yet crucial chemical variances furnish the inaugural concrete proof that comets from other stars mirror their specific natal settings. Enter 3IE Atlas as the third member of this rare group, boasting traits that render its antecedents appear ordinary. The carbon dioxide-heavy coma spotted by Spherex and validated by subsequent studies marks the greatest compositional anomaly among interstellar arrivals to date. The CO2-to-water ratio inferred from James Webb Space Telescope data points to even stranger birthplace conditions than those shaping Borisov. The distinctive sun-facing anti-tail of 3IE Atlas stands without precedent among earlier interstellar sightings. Whereas Oumuamua revealed no tails owing to its evident scarcity of notable outgassing, and Borisov showed the standard comet tails flowing outward from the sun. In contrast, 3I Atlas generates shapes that challenge the fundamental rules of comet behavior as established by hundreds of years of study. The sharp increase in brightness seen in September 2025 introduces yet another unusual feature to 3I Atlas's expanding array of peculiarities. Unlike Oumuamua or Borisov, neither displayed such striking quick changes in luminosity, which implies that 3I Atlas involves mechanisms, possibly outbursts of gas, alterations in form, or changes on the surface, happening over much shorter periods than those seen in other interstellar bodies examined before. When comparing sizes, patterns emerge among these visitors from beyond our solar system. Oumuamua's measurements, pegged at about 400 40 meters, make it bigger than your average tiny asteroids, yet smaller than the cores of most active comets. The core of Borisov was gauged at roughly 1 kilometer across, fitting right into the usual size for comets in our system. For 3I Atlas, figuring out its scale poses real puzzles, highlighting the unknowns about what it truly is. Data from the Hubble Space Telescope points to a core size ranging from 0, 3 to 5, 6 kilometer, covering both compact and fairly sizable comet cores. This wide spread stems from the challenge of isolating the core amid its vast surrounding haze, a trait all its own that sets 3I Atlas apart from earlier interstellar arrivals. The tools for chemical breakdowns have advanced a lot since each of these objects was first spotted, enabling ever deeper looks at their makeup. Oumuamua's short time in view and minimal gas release restricted studies to basic surface reflectivity and ballpark density figures. Borisov's more familiar comet-like actions allowed telescopes to pick up signs of water vapor, carbon monoxide, and a range of other molecules, as common in comet atmospheres. 3I Atlas gains from the cutting-edge tech brought to bear on any interstellar find so far. Infrared spectra from the James Webb Space Telescope, sharp images from Hubble, and earthbound sites with state-of-the-art spectrographs offer remarkable insights into its makeup, build, and changes over time. The paths of these interstellar guests also reveal tales of cosmic movements and the forces that fling materials from their home stars. Oumuamua came toward our solar system from near the star Vega, but its travel duration outlasted Vega's lifespan, pointing to a winding path across the galaxy. Its extra hyperbolic speed, the velocity it keeps after shaking free of the sun's pull, clocked in at around 26 kilometers. Borisov's path hinted at origins in a zone with young blazing stars in Cassiopeia, with an extra speed of about 32 kilometers. That faster pace could mean it was launched from a heftier stellar setup or boosted by gravity tugs along its cosmic trip. 3I Atlas holds the record for the quickest extra hyperbolic speed among such objects at roughly 39 kilometers. Such a high rate points to either birth near an especially hefty star or boosts from several gravity brushes while crossing the galaxy. This speed also affects how the object acts closest to the sun, as quicker motion cuts down the window for sunlight to warm deep into the core. The time between discoveries of these visitors sheds light on how common they are out there. Just 2 years separated Oumuamua and Borisov, then a 6-year wait until 3I Atlas, showing they zip through our inner system fairly often, but stay tough to spot because of their modest dimensions and fleeting appearances. Crunching the numbers on these 3 verified interstellar items reveals each stems from a distinct way of forming small bodies, pointing to vast variety in how alien systems craft and launch comets and asteroids, rather than sticking to standard traits. Every fresh interstellar arrival has broadened the spectrum of potential traits and ingredients. The standout features of 3I Atlas, like its massive haze extent, backward-pointing tail, molecular mix, and shifting glow, indicate that the variety among such wanderers includes surprises beyond what models drawn from our own system could foresee. Each one imparts fresh knowledge on how planets take shape across the cosmos, all while sparking fresh puzzles about the array of interstellar objects still to be uncovered. As 3I Atlas slips unseen through its closest solar approach, stargazers can merely ponder if the upcoming post-conjunction observations of 3I Atlas, are set to introduce fresh additions to the expanding list of oddities associated with interstellar objects. Trends observed in Oumuamua and 2I Borisov imply that 3 Atlas will keep astonishing scientists through actions that defy core principles of small body dynamics. Insights drawn from these three cosmic intruders reveal that the Milky Way generates minor bodies via mechanisms much more varied and intricate than the ones at play in our own solar system. Every such visitor bears traces of its chemical makeup and physical properties from its birthplace. These two detected entities hail from settings vastly unlike our stellar surroundings, offering tangible glimpses into how planetary systems develop across the galaxy. Section 12 addresses lingering scientific mysteries and ongoing discussions. The astronomy community's handling of 3I Atlas unfolds like a mystery tale, with vital proof concealed, compelling experts to build explanations from partial hints, as the key details stay obscured by the sun's intense light. Several rival theories seek to account for the comet's atypical traits, yet everyone sparks additional queries that might stay unresolved without or beyond data from after-conjunction studies, which could supply the essential elements to this extraterrestrial enigma. Debates over the core's dimensions and form highlight the core hurdles for investigators of 3I Atlas. Data from the Hubble Space Telescope has refined the diameter estimate to a span of 0.32 to 5.6 kilometers. Nevertheless, this wide interval underscores the challenge in distinguishing the dense core from its broad envelope of gas and dust. Such ambiguity is crucial since dimensions influence estimates of weight, compactness, exposed surface for vapor release, and resilience under the extreme warmth at closest solar approach. Varied assessment methods yield inconsistent outcomes. Models using heat derived from infrared data point to a compact core with elevated albedo, a bright coating that readily bounces back solar rays. In contrast, examinations in visible wavelengths suggest a bigger, dimmer core that soaks up greater amounts of sunlight. This mismatch might stem from uneven surface materials, errors in measurements, or basic errors in grasping how 3I Atlas reacts to solar warmth. Probes into its makeup encounter their share of inconsistencies. Spectra from the James Webb Space Telescope distinctly pinpoint carbon dioxide as the primary icy component in 3I Atlas's surroundings, where CO2 levels surpass water ice by substantial amounts. Such a profile starkly contrasts with typical solar system comets, in which water ice usually leads the volatile mix. Still, the prevalence of carbon dioxide poses conceptual issues for interpreting other noted features. The greenish hue that emerged in September often signals emissions from diatomic carbon. Yet, outflows heavy in CO2 do not inherently generate the carbon-based substances that cause that green glow. Either the spectral scans overlooked key ingredients, or the hue arises from dynamics more elaborate than basic molecular shining. Observations via ground telescopes like the Very Large Telescope and other premier facilities have spotted further molecular types, such as cyanide variants and assorted organics. These findings suggest a chemical richness that goes past the CO2 emphasis seen from orbital instruments, indicating that 3I Atlas holds a wide array of straightforward and intricate carbon-containing materials. The backward-pointing tail stands out as the most baffling visual enigma. Standard comet mechanics hold that sunlight's push should drive gases and particles sunward, forming tails that extend straight out from the sun's position. 3I Atlas seems to break this basic rule by expelling matter that builds features aimed at the sun instead of trailing behind it. A fresh theoretical study by Dr. Keto and Dr. Loeb, now in peer review, argues that the backward tail emerges from atypical sizes of dust grains paired with particular launch patterns from the core. Their framework posits that hefty dust bits released toward the sun with enough starting speed can resist the sun's radiative force, yielding the seen sun-facing formations. That said, alternative frameworks rely on distinct physical processes. Certain experts argue that electric forces exchanges between ionized dust and the sun's magnetic lines might steer particles in surprising paths. Additional ideas claim that 3I Atlas's spin creates uneven heating, focusing vapor bursts in targeted zones irrespective of sunlight pressure. The spin cycle of 3I Atlas stays undetermined after extended monitoring efforts. Photometric curves, used to gauge efforts to detect rotational periods in the comet through its irregular brightness fluctuations, stemming from an uneven nucleus turning under solar illumination, have yet to yield distinct periodic patterns. The lack of evident spin indicators might point to extremely sluggish rotation and almost round form or intricate spinning dynamics that mask straightforward cyclic changes. The comet's spin status influences various elements of its dynamics. Fast-rotating bodies encounter centrifugal effects that alter gas emission profiles and overall integrity. In contrast, comets with leisurely spins exhibit thermal contrasts between illuminated and shadowed hemispheres, leading to focused release of ices in warmer zones. Uncertainty surrounding 2I Borisov's rotation hampers attempts to simulate its heat progression and forecast upcoming activity. The luminosity surge recorded in September poses its own analytical hurdles. Various monitoring groups verified that 2I Borisov outshone model forecasts by a wide margin, though the extent of this outlier continues to spark discussion. Certain watchers describe surges in brightness spanning multiple magnitude steps, whereas others propose subtler boosts consistent with typical comet fluctuations. These inconsistencies stem in part from observational constraints. Positioned close to the sensitivity thresholds of many instruments, 2I Borisov defies precise light measurements even in ideal setups. Observers employed diverse reference stars, photometric filters, and data processing methods which can inject biases into luminosity assessments. At a deeper level, the scarcity of prior reference data hinders the examination of light trends. In contrast to recurring comets tracked across several orbits, 2I Borisov offers just one observational window devoid of past records for benchmarking. Scientists depend on simulations derived from local solar system comets to gauge anticipated patterns, yet such frameworks might not suit visitors from distant stellar systems. Investigations into its provenance seek to reconstruct 2I Borisov's path retrograde across the galaxy to pinpoint its likely origin point. Present motion studies imply it arose in the Milky Way's thin disk, the planar, star-dense layer hosting the bulk of ongoing stellar birth. That said, errors in positional and speed data amplify over backward time projections, resulting in expansive uncertainty ovals that span numerous potential natal areas. Debating its galactic roots carries weight for decoding 2I Borisov's makeup and antiquity. Ejecta from nascent star clusters may preserve distinct elemental traces compared to those from mature, processed stellar zones. The prevalence of carbon dioxide could stem from assembly in a protoplanetary disk marked by varying heat and chemistry. Diverging from norms seen in solar system bodies, debates also swirl around its structural coherence. The broad dust envelope and opposing tail imply intense gas release, signaling perhaps a nucleus brimming with ices or one facing breakdown. Certain experts suggest 2I Borisov comprises a loosely aggregated pile of fragments, a gravel heap sustained by feeble self-gravity, prone to crumbling amid heat or gravitational strains. Other theories view it as a solid body featuring atypical exterior traits or inner makeup that generates the noted emission behaviors. This differentiation is key for anticipating actions around closest solar approach when heat loads and gravitational pulls peak. The abrupt activity onset at 2 astronomical units, noted in early September, stays enigmatic. The sharp uptick in output as 2I Borisov pass this solar separation might signal the triggering of certain ices that vaporize at defined warmth levels. On the other hand, it could signify nucleus alterations that unveiled insulated ice reserves to sunlight. Distinct ice types vaporize at varying solar distances, forming an inherent activation order. Nearing perihelion, H2O ice ramps up emission near 3 astronomical units, whereas CO2 stays operative far beyond. 2I Borisov's particular responses hint at a multifaceted blend of ices with vaporization thresholds unfamiliar from local comets. The viewing blackout amid solar conjunction adds further doubt regarding which explanatory frameworks fit best. Pivotal validations of rival ideas, such as reactions to peak insolation, signs of breakup, shifts in emission, will unfold mostly beyond terrestrial sightlines. As 2I Borisov reappears post-conjunction in late November, scientists will confront the task of deciphering. Observing an object that might have undergone profound alterations during its hidden journey near the Sun presents unique challenges, as post-conjunction views could either confirm existing theoretical frameworks or spark fresh enigmas demanding novel interpretations. Discussions in the scientific community about 3 Atlas highlight the wider difficulties in deciphering rare events that strain the boundaries of detection technology. Every data point involves inherent uncertainties, every theoretical construct relies on premises, and every analysis needs to consider the chance that objects from interstellar space follow physical laws unfamiliar from our solar system's repertoire. Part 13. Natural Explanations. Prior to exploring highly imaginative scenarios, researchers insist on thoroughly investigating unconventional yet feasible natural mechanisms behind 3 Atlas's perplexing actions. Though the comet might defy present comprehension, it probably adheres to established physical principles just under such intense circumstances that humanity has yet to witness them. The prevalence of carbon dioxide in 3I Atlas's coma offers an initial insight into its extraterrestrial character via standard cometary studies. This makeup indicates origins in a zone around its parent star where conditions stayed cold enough for CO2 to solidify into ice, even as water stayed mostly gaseous. These scenarios generally arise past the so-called carbon dioxide snowline, the radial point from a star beyond which CO2 shifts from gas to solid. Within our solar system, this boundary sits far beyond the zones producing most comets. Consequently, local comets feature water as their main volatile, with CO2 in a supporting capacity. Yet, alien stellar systems might exhibit varied thermal gradients, star brightness levels, or elemental mixes that shift the CO2 snowline into areas ripe for substantial comet development. A dimmer star than the Sun could draw the carbon dioxide snowline nearer, enabling CO2-heavy comets to emerge in orbits akin to those yielding water-rich ones here. On the other hand, a star with an altered elemental balance, say, higher carbon compared to oxygen, might generate protoplanetary disks, favoring CO2 buildup over water ice, irrespective of heat levels. This origin theory not only accounts for 3's atypical makeup, but also its intensified outgassing patterns. CO2 transitions directly from solid to gas more easily than water ice under identical conditions, possibly yielding emission velocities far surpassing those of water-led comets. Such heightened activity might justify the swift luminosity surge noted in September and the exceptional coma extent captured by SphereX. Still, the CO2-heavy profile by itself fails to clarify the sun-facing anti-tail that has confounded experts since early high-resolution photos surfaced. Here, the dynamics of dusty plasmas come into play, blending solid particle behavior, fluid motion, and electric-magnetic interactions. Solar UV light-stripping electrons from coma gases forms plasma, a mix of charged entities sensitive to gravity and magnetic influences alike. This charged gas engages with electrified dust motes in intricate manners, fostering organized patterns beyond basic models of gravity and light pressure. Electrified grains can align into flows, threads, or helical forms under solar wind magnetism. In certain setups, these magnetic forces could overpower light-driven repulsion, directing matter along paths that seem to defy standard cometary rules. Thus, anti-tails might orient sunward even as typical tails extend oppositely. Support for this plasma-based view strengthens when factoring in 3I Atlas's boosted emission levels. Denser gases boost chances for charging and particle swaps that heighten electric effects. The odd chemistry could further shape plasma buildup via molecules that charge faster or differently than solar system norms. The object's spin dynamics provide yet another path to rationalize 3I Atlas's odd traits using familiar physics in harsh settings. A core turning extremely slowly might foster stark thermal contrasts between illuminated and shaded hemispheres, localizing gas release to targeted areas instead of spreading it evenly. Should 3I Atlas spin? The leisurely pace of its spin means the sun-facing side heats up to levels far beyond those typical for comets in our solar system, potentially leading to thermal swelling and gas buildup that propels streams of matter outward at speeds sufficient to resist the sun's radiative push toward the star. This setup would favor material spewing sunward from the warmest spots on the comet's core. To account for why 3I Atlas spins unlike most comets under this slow turn theory, one must consider the distinct developmental paths interstellar wanderers undergo while traversing between stars. Encounters with cosmic dust grains, gravitational nudges from nearby stars, or entanglements with magnetic fields might tweak spin rates in manners absent for bodies confined to one star's domain. The greenish hue emerging in September poses its own puzzles for straightforward accounts. While C2 molecules usually generate green glows in comet atmospheres, early spectral scans revealed scant signs of carbon-rich compounds beyond CO2. Yet, the idea of a critical threshold posits that C2 emission ramped up notably only as 3I Atlas passed a key heat or sunlight intensity mark around 2 astronomical units away. Such a tipping point might stem from the solar UV rays splintering CO2 into CO and oxygen atoms. Subsequent UV breakdown of CO could then yield the carbon atoms needed to form C2. This sequence demands particular light exposures and molecule concentrations that likely weren't in play during 3I Atlas's first sightings, but emerged as it drew nearer the sun's path. Other pathways for carbon involve intricate organics lurking in minor amounts inside the core, emitting detectably only under precise stimulation. Things like polycyclic aromatic hydrocarbons, amino acids, or varied organics might fragment under harsh solar rays, releasing carbon pieces that shine green. Differences in surface makeup provide yet another organic rationale for 3I Atlas's odd traits. Instead of assuming an even core throughout, the body could feature distinct zones with varied chemistries, some loaded with CO2, others holding water ice, and more sheltering elaborate organics. As 3I Atlas nears the sun and fresh surface areas warm for the first time, these compositional shifts might drive evolving gas releases. The early CO2 prevalence could signal the quick rousing of the most fragile outer layers, whereas prolonged warming might uncover deeper stuff with alternate builds. Porosity and inner makeup also shape comet actions in ways that could clarify 3I Atlas's quirks. A spongy core, basically a fragile clump of ice and grit bound by feeble bonds, might let sunlight burrow deep, stirring buried volatiles usually shielded from outer heats. This high porosity notion covers both the vast atmosphere and the swift luminosity shifts. Profound warming mobilizes bigger swaths of volatiles than in denser comet hearts, yielding gas outputs that outstrip forecasts relying solely on skin-deep heating. The interstellar trek of 3I Atlas across stellar voids may have wrought changes in form unseen in homegrown solar system relics. Blasts from cosmic rays, hits from interstellar grit, or heat swings amid varied radiation zones could reshape core traits, affecting how it responds upon hitting a star's fierce glow. The prime account for 3I Atlas's standout antics likely blends these organic mechanisms at work together. A CO2-heavy makeup fuels boosted venting. Plasma dynamics forge the backward tails. Gradual spinning focuses outbursts in targeted zones, and intricate reactions yield the noted hue shifts. Though each mechanism fits established physical laws, their interplay amid the harsh setup of an extrasolar comet's arrival could spawn effects that seem implausible, viewed solely through familiar solar system lenses. 3I Atlas might stand as an utterly bizarre comet, not some truly otherworldly thing, yet that strangeness positions it as exactly the sort of find that could upend insights into minor body dynamics across the cosmos. Part 14. Outlandish and edge case ideas. Here, we step into realms where sci-fi brushes against wild conjectures. At the point where scientific observations of celestial events start to merge with more imaginative accounts, the line separating ordinary cosmic occurrences from remarkable theories becomes indistinct. Although solid proof is lacking for these unconventional views on the comet 3I Atlas's actions, its remarkable traits encourage the sort of conjecture that has always followed mysterious sky events across the ages. Such notions function not as rigorous scientific proposals, but as imaginative exercises that highlight the peculiar nature of this cosmic traveler. The idea of an extraterrestrial signal device stands out as one of the most enduring far-fetched accounts for odd space objects. From the moment Oumuamua's finding ignited discussions on man-made sources, every fresh interstellar arrival prompts guesses about hidden tech indicators. The swift increase in luminosity, peculiar backward-pointing tail, and intensified gaseous envelope of 3I Atlas might, in theory, signal the startup phases of an automated explorer built to react to starlight conditions. In this signal theory, 3I Atlas appears as a sleeping tech relic that stayed powered down over its vast trek across space, safeguarding energy and form until hitting triggers for built-in startup routines. The surge in brightness during September may indicate when sunlight hit a threshold strong enough to awaken inactive components. Meanwhile, the backward tail could suggest targeted bursts of energy or substance releases tied to some engineered function. That said, this tech-based view runs into quick obstacles against actual data from telescopes. Data from the James Webb Space Telescope and Earthbound facilities reveal unmistakable traces of typical icy materials, like carbon dioxide, water steam, and carbon-rich compounds, aligning perfectly with what we'd expect from a regular comet's emissions. Investigators have found no odd isotope mixes, synthetic substances, or power patterns linked to sophisticated devices. The notion of a quasi-biological plasma entity pushes speculation into even wilder realms, building on studies of intricate plasma dynamics that can show apparent order in certain setups. Lab tests have shown that grainy plasma's blends of ionized bits and tiny solid flecks can arrange themselves into forms that echo traits of living things. Such plasma clusters can replicate, adapt, and adjust to surroundings in manners that vaguely parallel life. A few scientists have pondered whether elaborate plasma setups could emerge on their own in cosmic voids, perhaps showing actions akin to basic organisms. The erratic gas releases, backward tail forms, and reactive glow-up in 3I Atlas might hypothetically stem from these plasma-driven occurrences. This plasma life idea proposes that the void between stars could host patterns ruled by physics utterly unlike the chemistry of carbon life. These imagined forms could lie inactive across star-hopping voyages, only springing to life near a star's magnetic field, yielding visible changes that imitate yet don't equal true life activities. Still, this account demands physical processes that are entirely conjectural. True enough, grainy plasmas do create elaborate shapes in controlled experiments, but applying that to something as large as a comet navigating solar winds demands leaps well past what we know today. Nothing in the observations points to 3I Atlas displaying the electromagnetic traces we'd anticipate from major plasma groupings. The deliberate explorer story turns 3I Atlas into a deliberate survey operation from a distant stellar realm, featuring scripted responses meant to probe our solar setup as it sweeps through the core zones. Here, the comet's quirks are seen as deliberate designs. The broad gaseous halo could enable detection tools or signaling reach, as the backward tail might serve as broadcast gear directed at far-off listeners. Under the explorer theory, the glow-up of 3I Atlas signals not haphazard gas vents, but deliberate powering of monitoring and messaging gear as it nears key objectives. The spike in operations close to Mars and at closest solar approach might follow planned inspection steps, not just heat-driven reactions. Such a view sparks poetic musings on 3I Atlas, rousing itself amid our star system's energy profile. Its engineered awareness awakening following eons. Dormant interstellar voyages represent one possibility. The greenish hue could signal the activation of inactive detectors, whereas the quick shifts in luminosity may point to computational operations and signal broadcasts. Yet, this reconnaissance idea encounters identical proof-related hurdles as the artificial signal theory. The molecular traces, heat patterns, and build details of 3I Atlas align with projections for organic entities, though atypical varieties. Nothing points to computational functions, targeted messaging, or behaviors typical of engineered devices. The notion of unconventional substances posits that 3 Atlas harbors elements or functions via physical laws unfamiliar to modern knowledge. Concepts in theoretical physics outline options for bizarre matter types exhibiting odd traits, engagements with dark matter, altered gravity dynamics, or quantum influences at large scales that might yield visible effects diverging from established physics. Such unconventional material might account for 3 Atlas's peculiar anti-tail via gravity irregularities that alter particle streams or justify its intensified emissions via power discharge methods outside standard reactions. The swift intensification could stem from unusual state changes or energy reservoirs functioning under undiscovered physical rules. This account permits organic events that still surpass present comprehension, implying that 3I Atlas embodies not constructed devices, but innate mechanisms tied to physics humanity has yet to explore. The entity might act as an unplanned test site for examining physical laws absent in Earth-centric experiments. The time-based irregularity idea delves into the wildest realms, proposing that 3I Atlas could embody a form of data or substance movement spanning vast temporal spans. Imaginative tales from sci-fi depict the comet as a dispatch or relic from our future, dispatched rearward via tech that evades standard cause-effect limits. Under this view, 3I Atlas's odd features serve as signs of time alteration instead of journeys across stellar distances. The body might hail from a later iteration of our solar setup, bearing data or components meant for our present era. Its bizarre conduct could arise from clashes between advanced future tech and today's physical settings. Still, time-bending ideas demand laws not just unverified, but opposing core tenets of cause and energy balance per current views. No data indicates that 3I Atlas breaches preservation rules or shows time quirks past routine relativity impacts for fast-moving items. A skeptical lens on these outlandish accounts stresses how frequently baffling celestial events gain everyday rationales once ample info surfaces. Early pulsar finds fueled guesses of crafted pulses from superior societies, yet these turned out to be swiftly spinning neutron remnants. Sudden radio pulses ignited comparable discussions prior to linking to innate cosmic occurrences. Past patterns imply that 3 Atlas will eventually gain rationale inside familiar physics, perhaps via unseen mechanisms or settings. The comet's distinctive traits probably mirror the vast array of environments in distant stellar realms, not signs of bizarre laws or man-made constructs. The merit of probing these conjectural tales rests not in their likelihood, but in how they underscore the comet's true rarity amid human cosmic observations. An entity capable of prompting serious thoughts on extraterrestrial devices, plasma life forms, and strange materials marks a truly novel addition to our grasp of wanderers from beyond. As 3I Atlas proceeds through its obscured closest solar approach, these far-fetched rationales remind us of the vast unknowns in the cosmos outside our home system. Irrespective of whether the comet exits its alignment as a plain, albeit quirky body, or keeps showing traits that defy standard accounts, it has already broadened the limits of feasible interstellar arrivals. Part 15. Timer and Consequences. The universal timer advances to key instances that will shape not just 3i Atlas's self-disclosures, but lessons on the wider array of drifters across the stars. Every forthcoming benchmark stands as a vital trie. This interstellar comet, designated 3i Atlas, challenges the boundaries of our knowledge, observational tools, and capacity to derive valuable insights from events that strain the edges of modern astronomy. On October 3, 2025, it reaches its nearest point to Mars, about 30 million kilometers away, a pivotal moment in its journey. This flyby offers our species the prime chance to keep tabs on the rogue wanderer just as terrestrial observatories start struggling to spot it. The probes circling the red planet will push beyond their planned purposes, testing hardware limits to snag photos and spectral data from something hurtling by at cosmic speeds. Outcomes hinge on factors we can't dictate. Should 3i Atlas hold steady or boost its glow from current levels, the Martian satellites could reveal intricate views of its core makeup and the behavior of its surrounding haze details lost to Earth observers. But if it dims after its September surge, even the finest onboard sensors may pick up just faint traces, too weak for solid research. Toward the end of October, the comet hits its solar closest approach, perihelion. Between October 29th and 30, roughly 1/36 astronomical units from the Sun. In this intense stretch, 3i Atlas faces solar radiation that might spark the wildest shifts of its whole trip through our system. Peak warmth could unleash dormant icy materials that stayed intact during its star-to-star voyage, possibly sparking gas releases so vivid they reshape the comet's basic traits. Ironically, this peak happens right when 3i Atlas slips hardest to track from Earth, blinded by the Sun's overwhelming light that ground telescopes can't pierce. The universe's twist aligns the height of potential discovery with the nadir of our watching power. Any secrets unlocked at perihelion will mostly evade live viewing, captured only through lingering clues for future study. The blind spot lasts into early November, spanning 4 to 5 weeks when 3i Atlas drops out of sight entirely. This blackout hits during the predicted frenzy of activity, which could include breakups, wild luminosity shifts, or molecular changes that typically draw round-the-clock scrutiny. By early December, it resurfaces as its angle from the Sun widens enough for Earth scopes to rediscover and follow 3i Atlas post-conjunction. The version that reappears may look worlds apart from the one that vanished in October, perhaps fractured, far brighter or dimmer, or chemically transformed by the solar bake. The arc after perihelion opens doors for science well into the next year and further. Its swing by Jupiter in March 2026, though far looser than the Mars pass, could invite peaks from orbiters like Juno or the upcoming Europa Clipper, based on their positions and health. Lessons from such glimpses reach past 3i Atlas's quirks alone. Probing its alien makeup yields raw data on stuff born near distant suns, archiving details of the molecular setups in star-forming clouds across the cosmos. Its detected abundance of carbon dioxide points to birthplaces distinct from our own system's nebula, implying broader chemical variety in planet nurseries than we thought. Examining how the comet acts in harsh settings might upend views on ice vaporization, particle movements, and charged gas behavior in space. The odd anti-tail feature questions core ideas on comet responses to sunlight, maybe demanding fresh models that factor in overlooked magnetic influences. These findings ripple into larger debates on rogue bodies and their part in seeding chemistry galaxy-wide. As just the third verified outsider from beyond our stars, 3i Atlas's oddities hint that the Milky Way teems with more varied tiny world origins than models foresee. Every such intruder we probe adds key puzzle pieces to gauging how routine these cosmic drop-ins really are, examining the potential compositions of such fragments and their implications for environments in remote star systems. Analysis of fragmentation. Should the comet 3i Atlas experience disintegration near its closest solar approach, it could offer groundbreaking revelations regarding the inner makeup and material variations of interstellar visitors. Various pieces might hold substances from different layers of the initial core, essentially yielding samples from an entity that originated near a different sun. Patterns in how these fragments spread out, along with variations in their chemistry, might uncover architectural features that remain elusive from views of the whole body. It's important to temper expectations by recognizing the constraints of probing items that stay just barely visible, even in the best scenarios. 3i Atlas probably won't turn into a visible wonder for those watching from Earth without help, as its maximum glow is projected at magnitude 11 to 12, clear through a telescope, yet hidden from the unaided eye. While the absence of a striking show doesn't reduce its research worth, it does restrict chances for widespread public involvement, which frequently sustains funding and enthusiasm for space science. The European Space Agency's upcoming Comet Interceptor project, set to launch in the late 2020s, marks an effort to build quick-reaction tools for examining fresh interstellar finds. In contrast to standard space probes that demand lengthy preparation for fixed goals, Comet Interceptor will linger in orbit at the Earth-Sun L2 Lagrange point until an appealing visitor shows up, at which point it will adjust course to rendezvous and probe the intruder on its way through our solar neighborhood. That said, the mission's reach is hampered by the core issue of spotting interstellar travelers soon enough to arrange probe flybys. 3i Atlas was spotted merely months prior to its solar nearest pass, leaving too little lead time for any tailored spacecraft effort, assuming such fast action tech were available. Upcoming detection tech needs to flag these interstellar guests years ahead to make worthwhile probe meetings possible. Upgrades to Earth-based telescopes promise quicker gains for advancing interstellar object research. The Vera C. Rubin Observatory, now being built in Chile, is slated to start in the mid-2020s, boasting unmatched wide-sky scanning power. Its knack for scanning vast sky areas over and over again should catch interstellar objects far sooner during their solar system visits, allowing longer viewing windows and stronger chances for in-depth analysis. The observatory's main effort, the Legacy Survey of Space and Time, anticipates finding several interstellar objects annually after it ramps up fully. This surge in finds will shift interstellar studies from sporadic lucky glimpses to organized surveys of whole groups, tackling key issues about the galaxy's reserves of small bodies and how their makeup has changed over time. Advances in adaptive optics, spectral analysis, and orbital telescopes keep pushing the boundaries of insights from dim, fast-zipping objects like 3i Atlas. New massive scopes, such as the 30-meter telescope and the European Extremely Large Telescope, will deliver superior light collection and sharpness that might overhaul how we profile interstellar objects. The James Webb Space Telescope's infrared tools have already shown their worth in interstellar work, yielding makeup details beyond what older gear could achieve. Later orbital platforms tailored for minor bodies might enable non-stop tracking free from Earth's air interference, or times when the sun blocks the view. Global teamwork grows ever more vital as probing interstellar objects calls for synced efforts across diverse sites and regions. The observing push for 3i Atlas highlights both the promise and hurdles of rallying worldwide action to fleeting sky events. Insights from this joint operation will shape how we handle future such alerts. Sharing data and review methods crafted for 3i Atlas sightings are setting benchmarks for the astronomy field in managing fast-shifting top-priority events that demand instant input from various observing sites. These approaches will be key as interstellar detections rise and joint study windows multiply. The wider fallout reaches past astronomy into core puzzles about material forms and chemical processes across the galaxy. 3i Atlas supplies tangible proof of settings around other suns, locked in its untouched state. During eons of journeying through the vastness of space between stars, these forms have taken shape. Observations of each such wanderer help illuminate variations in planet-building mechanisms amid diverse stellar settings. Insights into astrobiology arise from examining these interstellar intruders as they could ferry organic molecules or rudimentary life across stellar realms. Although nothing indicates that 3i Atlas contains biological substances, its organic makeup might shed light on how intricate carbon-based molecules are scattered across the Milky Way. Finding amino acids, bases for nucleic acids, or additional prebiotic materials in these cosmic travelers would dramatically reshape our grasp of life's foundational chemistry dispersing through the cosmos. The atypical composition of 3I Atlas, though not inherently alive, illustrates how interstellar bodies can safeguard elaborate molecular frameworks over immense galactic spans. Aspects of planetary protection, irrelevant to 3I Atlas given its harmless path, gain from research on these objects, which refines knowledge of their responses to solar warmth. Upcoming interstellar arrivals could trace paths nearer to our world, demanding precise forecasts of their dynamics to evaluate collision hazards. The distinctive traits of 3 Atlas expose shortcomings in existing simulations for forecasting cometary actions, implying that defense frameworks need to incorporate categories of objects unfamiliar from our local solar neighborhood. Deeper comprehension of the physical properties of interstellar bodies may become essential for properly gauging dangers from prospective intruders that could present real perils. Efforts to involve the public with 3I Atlas underscore the hurdles and benefits of sharing frontier science with everyday viewers. The object's intricate details and dim appearance pose obstacles to widespread casual fascination. Still, its origins beyond our system and peculiar antics spark enthusiasm in those aware of its importance. Schools around the globe are weaving observations of 3I Atlas into lesson plans. By treating the comet as a live illustration of scientific breakthroughs and advancement, learners can track monitoring efforts, examine open-access datasets, and observe the progression of knowledge as fresh findings surface. The private space sector is growing more invested in probing minor celestial entities, valuing their research potential alongside economic prospects in profiling asteroids and comets. Though 3I Atlas offers no prospects for extraction or utilization because of its hyperbolic orbit, the methods honed in its study bolster wider skills for assessing small bodies that could hold commercial promise as we near those key October milestones. 3I Atlas has already proven that visitors from afar will repeatedly upend our preconceptions about the cosmos outside our home system. If the comet's upcoming actions validate prevailing ideas or unveil wholly fresh enigmas remains to be seen. It has set a fresh benchmark for the unforeseen in celestial events. The concluding narrative that will cement 3I Atlas's place in history hinges on revelations from the vital forthcoming weeks. 3I Atlases is starting to disclose its essence, a molecular relic from Mortine 6, another star, an experimental site for physics under unprecedented circumstances, or maybe an even grander marvel that compels an overhaul of our views on interstellar drifters. Over the coming weeks, it might blaze with unmatched brilliance, shatter into a shower of cosmic fragments, or glide silently by our star, hauling its mysteries into the void once more. And the outcome could profoundly alter our perspective on envoys from distant suns. For those equipped to pursue this stellar mystery tale, the invitation is straightforward. Keep an eye on image drops from ICE's Mars Express and Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter, and MAVEN. Then, anticipate the after-perihelion reports from Hubble Space Telescope and James Webb Space Telescope, which could at last uncover what 3I Atlas genuinely signifies. The cosmos has dispatched an emissary from a foreign sun, and soon will decipher its tidings.